Good morning, my name is Esteban Cambronero.
I'm Andrew Larhan.
I'm Mason Malone.
And I'm Rohan Singh, and we conducted research in the field of PaperBots. So just a brief outline of what we will be talking about today. First, we will be going over our purpose and background of our research. Then we will be going into the research that we conducted as well as the procedures that we followed in our experimentation processes. And finally, we will be ending with the conclusions that we drew from our experimentation as well as future thoughts and applications. So just a general purpose. Our general purpose was to construct a PaperBot that can aid in search and rescue missions in disaster situations. As you all may know, disaster situations are unpredictable and they can happen at any time. So although the responses at the moment are very effective, there's still a scope of improvement. Our PaperBot essentially goes in and finds civilians, and it can also go from the civilians to the outside to help search and rescue teams find civilians. And since it is autonomous, it can just be sent out both from within the affected area and from the outside of the affected area to find and help. And the advantage of these PaperBots are mostly due to the material that's used. So since it is made out of paper, it's very inexpensive. And this relates to its disposability. Since it's very inexpensive, if the PaperBot was to get damaged beyond repair, we can just dispose of it without much of an expense. Also, in terms of storage, due to the paper's collapsibility aspect, we are able to store large numbers of these PaperBots in a very low space. Also, hopefully in the future, we want to see mass production. Since there are very simple components in the PaperBot itself, we want to see if we can mass produce these in factories and hopefully scale them around the world so that one day PaperBots can be used in almost any application anywhere throughout the world.
So the benefits of using paper, it's cheap, readily available, there are different types, and it's versatile. What I mean by versatile is that it can be folded into strong structures, it can be bent into flexible shapes, and it can be enhanced, meaning you can use it in combination with tape or glue to improve its performance and ability. But the drawbacks are it's highly susceptible to water damage as water rips apart the cellulose fibers, which destroys the paper. It lacks the ability to withstand mechanical forces, and has a low durability, meaning that over extended periods of time, the robot's performance decreases.
So some of the experiments we drew to determine which type of paper would be the best to use. First we started with a compression experiment. So we took a compressed spring, as you can see in figure 2, and then elongated it to its maximum elongation and took these two measurements, comparing them to one another. Here you can see the data that we compiled. Origami paper was able to compress to 57 times its size. Printer paper was able to compress to 85 times its own size, and cardstock paper was able to compress to 31 times its own size. This was a very useful number as we needed to determine how we would build springs and other foldable materials. The second experiment we conducted was a weight supporting experiment. In figure 5, you can see a cardstock piece of paper supporting a predetermined weight. In figure 6, you can see the origami paper actually deforming as a result of the weight applied to it. In this data, you can see that cardstock was the clear winner with being able to support 170 times its own weight, with origami and printer paper at 65 and 40 respectively. This was important because we chose to make our chassis out of cardstock paper as it could support the most weight.
So we needed to create a chassis that is strong, lightweight, and can support electrical components. The first step in this was making a rectangular box that was big enough to hold all the electrical components, which you can see in figure 8. The next step was implementing supports that would increase the robot's ability to withstand mechanical forces. An example of support is seen in figure 9. And then for the robot to function autonomously, we needed sensors, and to attach these sensors, we decided to use the origami spring, seen in figure 10. The next step in the process of making the robot is implementing forms of locomotion.
For the actual locomotion, we chose to use wheels. So our purpose with the wheels was to fabricate rubber wheels able to support the weight of the robot, traverse rough terrains, and endure damage. We used a 3D printed mold and then cast the wheels using different types of rubber. Choosing the rubber was a difficult process as we had many options to choose from. We narrowed them down to 3, Moldstar 30, Moldstar 20T, and Sorta Clear 37. Each of these are ranked on a Shore A hardness scale, which is a hardness scale for soft rubbers. Moldstar 30 has 30, 20T has 20, and Sorta Clear 37 has 37, and we started with Moldstar 30 because it was a medium value. Another value that we chose to look at was elongation at break. So that's the second number in the column, and that number represents how far the rubber can stretch before it breaks. We chose to start with Moldstar 30. We saw that it was too rigid to start with. Then we moved to a combination of Moldstar 30 and Moldstar 20T. By combining these two, we were able to provide flexibility while also maintaining rigidity. We then started an experiment with Sorticlear 37 and Moldstar 20T, but the bonding between these two materials was incompatible. So our final decision was a Moldstar 30 for the outside rubber and Moldstar 20T for the inside rubber. The different types of rubber can be seen here. The outside of this wheel is Moldstar 20T, and then the inside, the white section, is Moldstar 20T. We had different sizes of the wheel. 2 large wheels were made and attached to the robot with motor supports, and then 2 smaller wheels were made, and those were attached to the bottom of the robot. It was very important to stabilize the small wheels, as we needed them to not touch the bottom of the robot, but also not touch the floor, as they were mainly for stabilization. The wheels were attached with studs piece of papers by rolling pieces of paper up and then adjusting them to a predetermined height so that the wheels would be able to stabilize the robot.
So the motor supports that were talked about previously are, you can see in figure 14. And when we experimented with motors, we tried 2 types of motors. Initially, we started with stepper motors. Now, stepper motors are easier to program with the Arduino program that we used. However, we realized that it lacked a lot of torque, so the vehicle actually didn't even move. Therefore, we decided to switch to geared DC motors. Geared DC motors require a 9-volt battery, and due to the limitations of the Arduino, which will be explained later, the 9-volt battery actually could not be connected directly to the Arduino. We had to connect it externally. So we ended up experimenting with the geared DC motors, and we determined that they were efficient enough to move the vehicle at a very fast pace. And so we also, in order to actually work the vehicle itself, we had to incorporate a motor controller, which had the L298PH bridge. The L298PH bridge allows for the vehicle to move both forward, backwards, and turn at different angles, as it reverses the polarity of different motors. So, for example, if I wanted to go backwards, I'd have to reverse the polarity of both of the motors. And without the motor controller, we would not have been able to do that. So, a little going into the microprocessor that we used, we decided to use the Arduino Mega. Initially, we started testing with the Arduino Uno. However, we realized that it's too small to support the ports that we needed. And some benefits of using the Arduino, we were already familiar with the Arduino program. So the programming language that the Arduino uses is related to C. And all of us had previous experience using the Arduino program, so it was not that hard to code these DC motors. Also, it was available and convenient to use. During our experimentation processes, we had to research a lot about how exactly these motors are going to work. We didn't have any other microprocessors available in the lab, so we just tested on small-scale experiments with the Arduino Uno, and when the Arduino Mega came, we just attached all the motors and all the sensors as well. Some drawbacks, however, one of the drawbacks is size constraints. So the Arduino Mega is relatively large, and because it's large, we had to make the vehicle bigger. Now, you want to have the smallest vehicle because you want to have less weight, and it's more efficient when it's smaller. So this was one of our drawbacks, and also electrical current limitation. So as I mentioned before, the DC motors require a 9-volt input, or 9-volt power source. The Arduino doesn't have, it only allows 5 volts to run through. So what we had to do was we had to send 5 volts through the Arduino to the sensors, and then attach an external 9-volt battery to the motors. And that you can see at our demo.
So for our actual sensor design, it's a 2-part design. The larger section on the right, as you can see in figure 16, is called the activator, and the smaller section is the receiver. The receiver detects as the activator moves close to it using a resistive capacitive touch sensor circuit, as you can see in figure 17. And as the activator gets closer and closer and closer and eventually makes contact with the receiver, that is registered as a touch. This allows the robot to navigate its environment after it makes contact with an obstacle. So for the robot's behavior, we built it around the relatively simple objective of exploring the disaster area to its fullest extent. Therefore, the direction of the motion is dictated by the sensors. As it hits the wall, makes contact, turns, and continues forward. So it's a relatively simple algorithm where the robot simply moves forward until it makes contact with something and evades or moves around it to continue moving forward. We initially tried to program this using a function-based model where in code we defined every motion as a function. So moving forward was a function, turning left, right, and moving backward were also functions, as well as reading each of the sensor values. When we did this, we ran up against the issue where there was a direct trade-off between the robot couldn't read the sensors and drive the motors at the same time because we hadn't defined it in code that way. So we switched to what's called a state-based model where every action that the robot is making is a state, 1, 2, 3, 4, for moving forward, backward, turning left and right. And the robot will change the state from one to the other based on the sensor readings and how long it's been in that state. So it can be set to back up for 2 seconds, turn for 1.5 seconds, and that allows it to actually navigate its environment. As you can see in the next slide, here's a demo of the robot's behavior. So here's our robot as it moves forward and eventually makes contact with an obstacle on the front right sensor. It switches to the reverse state, the turning state, and then the forward state yet again.
So we actually have a working video in figure 19, and in the final test, the robot was able to navigate through obstacles, sustain collisions, and we saw that the behavior was implemented correctly. In figure 19, you see the robot running into a couch, detecting it, and then turning away from it, avoiding the obstacle successfully.
So for our further research, we would like to explore more origami folding techniques to create a chassis that is actually compressible. As of now, our chassis is not. So we'd like to experiment with what's called the Miura-Ori folding technique, where the paper is folded into a series of parallelograms. This allows the paper to be highly compressible, and it has the unique property that when it expands in, say, the horizontal direction, it also expands in the vertical direction. This is somewhat atypical compared to a typical accordion fold where it only expands in one direction. This would allow for relatively simple mechanisms to expand and contract the robot in both directions. We'd also like to experiment with creating extreme collapsibility by reducing the size of certain inflexible components within the structure of the robot, such as motors and motor controllers. And on that note, move to printing actual circuit designs on pieces of paper that are foldable, which would allow for the rigid, inflexible circuit boards of both the Arduino and motor controller to be eliminated, which will make the robot overall much more compressible. For our long-term goals, we would like to see mass production, integration into disaster-prone areas, and composite data aggregation, which is basically the robot, each individual robot can be deployed to send data back to a search and rescue team, and that search and rescue team, with however many robots they've deployed, can aggregate their data and analyze the entirety of the data, allowing the team to create a full-scale map of their current disaster situation. We'd also allow for connection between different units, which would allow robots to eliminate redundancies in path traveling, so one robot doesn't go where another robot's already been, or have robots change for constantly updating scenarios where they can share data.
And we'd just like to acknowledge our project mentor, Mendez Singh, our RT liaison, Melissa Tu, Dr. Mazeo, Dean Antoine, the Assistant Director of the Governor's School, Dean Rosen, the Director of the Governor's School, Project Coordinator, Brian Lai, Head Counselor, Nicholas Ferrero, Rutgers University, Rutgers School of Engineering, the State of New Jersey, Lockheed Martin, Silverline Windows, Rubix, and other corporate sponsors, and USET alumni. Thank you, and any questions?
So the short video you showed us, that vehicle's autonomous. There's no joystick input from the user at all. It's all programmed per your design.
Yes.
Yep.
That's ingenious. I love it. Great.
Thank you. Yes, James.
So when you're storing them, and if you have a compressible model you can store, with the larger parts like the wheels and the Arduino controller, would they be not stored with it, or is your goal to store that all together?
Ideally, the Arduino controller would be removed from, say, its typical circuit board design and mounted directly on the paper, which is what I alluded to with the printed circuit boards on paper, which would allow the Arduino and the various other integrated circuits to actually compress with the paper. As for motors, those could theoretically be removed, and then the robot could be fully compressed, the motor stored alongside, and then everything connected back together for activation. Yes?
Did you guys think about modular programming, or you just went directly to Arduino programming? And the second part of that question is, if you did think about modular programming in mind, also think about incorporating machine learning as far as the fact that the robot can take information from the sensors and automate itself or to update itself, update its models, say, so that a more rapid way of increasing redundancies instead of programming the robots to keep away from redundancy, but machine learning will also teach itself to increase, develop its own anti-redundancy tactics like that.
So for this project right now, we had the time limitation of 1 month, so we couldn't actually implement machine learning. It would be relatively difficult to do on an Arduino microcontroller, seeing as it's much simpler than even the processor that's in your phone. Ideally, we would like to put machine learning on a larger computer that all the data is sent to. So individual robots send data back to the search and rescue team, and the entire search and rescue team has a computer which processes that data. And that computer could run machine learning algorithms on it, actually, and coordinate robots.
Thank you.
Thank you.